Bueno, continuamos con el simposio del doctor Jean-Francois. Vale la pena solo tener en mente recalcar lo de las medidas de seguridad y de igual manera, bueno, va a ser aproximadamente 1 o 2 horas. Después va a venir una persona relacionada a la embajada donde nos va a presentar sobre las oportunidades de hacer intercambio y colaborar con Francia. Entonces, mente abierta para preguntar sin pena. Y también vamos a tener un show de guitarra de nuestro gran amigo Ale, entonces para amenizar el rato. Y finalmente, pues las personas que tengan tiempo y disposición, vamos a cerrar con comida. Entonces, todos son bienvenidos. Y bueno, let's go. Thank you, Profesor.
Okay. Thank you, Saul. So we were saying that even metal surfaces are sometimes more complicated than expected. Here is another example. If I take the same platinum structure and now I cut along the 1,1,0 plane, C intersecting A and B, and parallel to C, I would expect to see a surface that looks like this, in which the atoms in a dark gray are in the first layer, and those here in light blue would be deeper in a second layer. Anyway, it would be a rectangular symmetry. And the unit cell of this rectangular symmetry would be this small piece here. When you look at it with, for example, scanning tunneling microscopy, what you see is somewhat different. Well, this would be just the same structure but repeated a few times more, and the experimentally observed reality is like this. This is not, of course, a real STM photograph, it's the reconstruction of the underlying surface. For obvious reasons, this is called the missing row reconstruction. You still have a rectangular symmetry, but the basic unit has to be larger. And here, it's like all of the atoms in the top layer had been removed from every second row. Where did they go? They didn't go up in the air, of course. They cannot vaporize. They just went to another part of the surface where they do the same thing, but at a higher level. Okay, this is very well, but is it relevant for the origins of life research? Yes, first, I had another example here, just to show you that some really complicated structures can really arise. This is chromium after exposure to gas phase dinitrogen. And what you see here is a real STM picture with, as you can see, a lot of structuring going on. Mostly these are still chromium atoms with a few nitrogen atoms here. And this is the reconstruction with the unit cell with the chromium atoms in various layers, higher or lower, deeper in the surface, and with the nitrogen atoms that contribute to the structuring here. So we already have a little adsorption, which is the next topic, but mostly I wanted to show you how complicated it can get. For obvious reasons, it's called the herringbone structure, because it looks like fish bones. And the structure forms units that are a lot larger than would be expected. There is some kind of information being created on surfaces. So I asked the question, is it relevant for prebiotic chemistry? Native metals are not usually invoked in prebiotic chemistry scenarios. There might have been a few isolated examples, but mostly the minerals of the early Earth were oxides. Can you do this kind of surface chemistry with oxides? Well, more or less. It's a lot more difficult, especially because if you want to do STM and some other techniques too, you need a conducting surface. It works well with a metal. It doesn't work with an insulator. However, there are some metal oxides that are sufficiently conducting. In fact, they are semiconductors, and that's enough to do STM of them. This is, for example, a picture of the surface of TiO2, of the rutile structure. And this is an STM picture. You see the spots representing individual atoms are not as well defined as what we have seen on platinum, but yet you can still recognize them individually. And these are, in fact, some rows of oxide O2- ions. And here too, just like on platinum, you can see some oxygen vacancies, which are certainly some sites with a very high reactivity. So we can do also a surface science on TiO2 for one. And here's an example of what can happen on TiO2 when this surface is exposed to water from the gas phase. Well, these would be the water molecules. And on the surface, the red circles are Ti4+ ions, and the blue circles are O2-. In the structure of bulk rutile, you have the Ti2+, Ti4+ that are surrounded by 6 oxide ions, 4 in this plane, 1 below, which is conserved, and 1 above it, which is not kept when you cut the surface. So what we get here is a so-called Lewis acidic structure, an electrodeficient ion that can react with a Lewis base, like water. Water has non-bonding electron pairs. And so water will have a strong tendency to adsorb on the exposed Ti4+. But when you do that, some electronic density is given to the Ti4+, and the OH of water become more acidic. And since right next to these acidic sites you have a basic site, O2-, you can have a proton exchange. And this is the resulting state. You see this water has lost one H+, and given it to the O2-, you are left with the 2 OH- hydroxide ions, but they are not in the same surrounding. This one is terminal on a single Ti4+ ion, and these are bridging between 2 Ti4+ ions. How do we know that this happens? Well, we can see it with another technique, with infrared spectroscopy in this case. In the infrared, the terminal OH will resonate to different position than the bridging OH-. So when we see that, we understand that this chemistry has really happened, and indeed it's a quite logical chemistry. So these are just 2 examples of surface chemistry. And I had first written sources of diversity, but I think this word should not be used anymore. According to Mr. Trump, you can as well say surface complexity. There are many different sources of complexity on surfaces. First, you can have different crystal phases, even of the same material. If you take silica, for example, among others, you have cristobalite and you have quartz. And this translates in the existence of different types of surface groups. Silica can be understood as a mostly covalent bonding between Si and O. The O are bridging between 2 Si, and the Si are 4 coordinated. If you cut a surface in silica, you will form, to keep electron neutrality, you will form some SiOH, some silanol groups. But these silanol groups can be very different according to the crystal phase. And here you see that on cristobalite 101, which looks like this, the SiOH actually they are close enough to each other to make H bonds, SiOH, OH, and these H bonds form a one-dimensional chain. Here in the middle I have quartz. Quartz 001. Now the structure is different, and the SiOH that are formed by cutting the plane are geminal. There are two on each silicon. And it results in forming geminal chains that are connected to each other, not only in one dimension, but also to the neighboring chains. And finally, and here I'm anticipating on the next slide, this is also cristobalite, but it's a different plane. Here, the geometry is different. The OH groups, the silanols, will also be formed, but they will be too far from each other, and they will not be able to interact and to form OH groups. They will be isolated silanols. And each one of these patterns has a different reactivity for adsorption. Now, as we have already seen for cristobalite, if you are looking at different crystal planes of the same structure, of the same crystal, you will not have the same arrangement of atoms. And for slightly different examples here, on gamma alumina, which is a spinel oxide for those who know crystallography, if I cut it along 110, I will get something like this. The gray circles are underlying O2 minus. The aluminum ions are not seen because they have made some bonds with either H2O or OH groups, and you see that you will get some very different surface groups here. H2O coordinated to a single aluminum, and OH between two aluminum atoms. Furthermore, the environment of the aluminum atoms is tetrahedral here and octahedral here. So you have these two types of surface groups. They have some names. They are called 1A and 2B. But if you cut the same crystal structure along 111, you will get a different set of surface groups. Here you have the same 2B bridging OH that we have seen on the other face. And here is something new. It's an oxygen that will be capping between three aluminum ions. And because these three aluminum atoms will withdraw a lot of electron density from the OH, it will be very easily deprotonated to O minus. So you see, you get a different type of site with a different reactivity. Now, another source of difference between surfaces is the surface charge that they bear, as you can understand from the previous slide, in which you had some positively charged and negatively charged surface groups. In a way that's possibly easier to understand, clay minerals are layered materials, and they have layers that bear a negative net charge. So this has to be compensated, and it's compensated by some exchangeable cations between the clay layers. So we have a negative charge. On the zeolites, we also have a negative charge resulting from substitution. On the other hand, on layered double hydroxides, they are in a way reverse clays. They are called anionic clays. Why? Because the layers have a net positive charge due to atomic substitution. And because they would not be able to exist with a net charge, it's compensated by anions between the layers. So you have a negative a negative network charge in the case of clays, compensated by cations, and you have a positive charge compensated by anions in the case of layered double hydroxides. Now, in the case of silica and alumina, what you have is a pH-dependent electric charge, but we'll come back to it a little later when we speak about adsorption. Yet another source of variation on surfaces is the existence of porous structures. Pores, simply little holes, can exist and be of the same size as ordinary molecules, a few angstroms to a few nanometers. That's the case in zeolites. Here you have bottlenecks between the large pores here in the middle. You have some bottlenecks or windows that have a size of 7.6 angstrom. That's called microporosity. And here you have the recently developed mesoporous silicas, in which you have mesoporosity. The size of the pores is about 10 times higher, now in the nanometer range. These two structures also differ by the connectivity of the porous network. Here it's three-dimensional. You have windows in the X, in the Y, and in the Z direction. And here it's one-dimensional. It's like some very elongated tubes. And finally, you can have macropores, just like in pumice, you know, the volcanic stone, in which the pores can be as large as a few millimeters. All of these have been invoked in origins of life scenarios. Now, a very particular type of porous structures is clay minerals. So, I don't know, maybe you are familiar with them already, but they are layered materials and they are composed of octahedral and tetrahedral sheets in which you can have a lot of compositional variability. So, for example, if you had silicon in each tetrahedron and magnesium in each octahedron, this would give some neutral layers. If you substitute Si4+ by Al3+, there is one positive charge missing. That means one negative charge. And this is why clay layers bear a negative charge. So one source of variability is in the atomic composition, but something very interesting is also the type of porosity. Between two successive layers, between two flat layers that expand for maybe several microns, you have the interlayer space here, and it can be expanded. If you have a large molecule and you have some kind of driving force to make it come inside the clay layers, well, it can increase the spacing. It's tunable porosity, if you wish. So that's yet a different type of porous structures. Okay, now let's speak about adsorption, because it's very well to know that the surface looks like this or like that, but it would be only theoretical knowledge if it was not reacting, if it was not doing something with molecules from the outside world. So when this happens, we speak about adsorption. And adsorption is often studied in very different ways, using different terminologies, but basically it means any kind of chemical reaction that results in the binding of a species from the gas phase or from some solution phase to the surface of a solid. Of course, as we will see, it's a required step if you want to do heterogeneous catalysis. Some of the species must get adsorbed at some time. And that's one good reason to study adsorption, but there are many others if you want. For example, you have soil solution that is polluted by heavy metals, you want to understand how they will interact with the minerals in the soil. And that would also involve some adsorption reactions. They might result in immobilization of the heavy metals. Adsorption can be studied just like all surface phenomena at the macroscopic level, in which case we will use some methods of thermodynamics, and also at the molecular level. In terms of thermodynamics, it's often useful to define what we can call a surface phase. So between the underlying solid and the gas or the liquid phase, there would be a surface in which some molecules can get concentrated, for example. And so we can define an activity of these molecules, but they would not be in molecules per liter, but in molecules per unit of surface, in molecules per square meter, for example. And they would be denoted by the curly brackets in what follows. So I'll just give you a short example of the kind of approach that is used to understand adsorption phenomena. There will be a little thermodynamics and thus mathematics here, but it's not very important to follow in detail. It's more important to have the general idea of the way these phenomena are being approached. The simplest and one of the oldest models is the Lambert model of adsorption. You have to define a model by positing a number of hypotheses, simplifying a hypothesis. If you get a mathematical expression out of this model, and if it fits the data, then you will conclude that the hypotheses were correct. And what are they here? First, you will define some adsorption sites. What are the adsorption sites? You don't need to know. It's probably a certain arrangement of atoms on the surface that is able to bind a molecule. But you will just denote it as a little star. And you will suppose that they are all equivalent, and as a consequence, they will all interact in the same way with molecules from the liquid or gas phase. And you will also suppose that the adsorbed molecules do not interact with each other, only with the surface. Okay? So this is certainly a gross simplification. You can write the adsorption reaction just like that. A molecule, for example, from the aqueous phase will react with this little star which is on the surface to give you some kind of association. What is this? It could be a covalent bond, but it doesn't have to be. It could be a hydrogen bond or whatever. Then you will just define an adsorption constant for this adsorption reaction. And you remember basic thermodynamics. We have to write the adsorption constant in terms of activities of the species in this equation. We will take the activity of what is on the right-hand side, but that's on the surface, so it's in molecules per meter square, divided by the activity of free sites, those that are not bound to A, also in the surface, and the activity of A, but it's in the aqueous phase, so it's a regular concentration. Also, you will remember from basic thermodynamics that the equilibrium constants depends on the free energy difference in the reaction. And in this case, it will be the free energy of adsorption. It can be called the adsorption strength, if you wish. So we have two parameters here. The first is B, and the second is the number of adsorption sites on the surface. That's a two-parameter model. Now I will go quickly over the derivation. This should be theta A. It's a fractional coverage. I don't know why something disappeared here. And it's expressed as the number of adsorbed molecules divided by the total number of sites, either occupied or unoccupied. In that case, you can rewrite the expression for B in terms of theta, and it will be like this. This is related with the adsorbed molecules, and 1 minus theta is related to the sites that remain free. And it's a simple first degree equation that can be solved for theta, giving you the Langmuir isotherm, how to express the amount of molecules adsorbed in terms of the amount of molecule in the solution, in this case, the concentration in the solution. If you want, instead of theta, you want the real number of A adsorbed, you just multiply by n max. Okay? And what does it look like? Like this. This is a typical Langmuir shape. If you plot the amount adsorbed as a function of the concentration in solution, you get something that shoots up like a straight line. Then there is here an inflection, and then it goes asymptotically to a maximum value where all the sites are occupied. How quickly does it go to this asymptotic value? It depends on B. If B is high, it will look like this. If B is low, it will look like this. Well, so sometimes it's not obvious to recognize from these isotherms if the data follow a Langmuir model or not. But you can have an easy check of the validity of the model by taking the so-called Langmuir transform. Instead of n adsorbed, you take the inverse value here and you plot it as a function of the inverse of the concentration. And from the preceding equation, we see that the dependence should be like this. It should be linear with the intercept giving you the maximum number adsorbed. And from the intercept and the slope, you can calculate B. So the Langmuir transform will look like this. In this case, 1 over n max is very small. It's very close to 0. So we have a simple model that depends on simply the number of sites per square meter and the adsorption strength. And as I told you, the second parameter, the adsorption equilibrium constant, is related to the free enthalpy difference of the adsorption, denoted like this, by this very general relation, one of the most important in chemistry, in my opinion. B is equal to the exponential of minus delta G0 over RT, knowing in addition that delta G0 has two components, an enthalpic component, which is related to the adsorption heat, and an entropic component. If you have a strong adsorption, that means you have a high value of B. That means you have a very negative value of delta G of adsorption. A in solution would be higher than A adsorbed, either because you have a negative energy of adsorption, or because you have a positive entropy of adsorption, or any combination of the two. So you can check all of this by simply doing macroscopic adsorption measurements. As I have already said, take a solution with a known amount of E, contact it with the solid phase, and you will see the amount of A in solution decrease because some of it is adsorbed. If you have some spectroscopic or other means of measuring A in solution, From the difference, you will deduce the number of molecules adsorbed, and you can plot it as a function of the concentration. And you can learn some interesting things on the strength of adsorption. Or, for example, here I have taken a theoretical case in which it would be a little more complicated. You would have two families of sites, two different little stars with two different adsorption strengths. There would be the sites with weak adsorption, represented here in red, and the sites with the strong adsorption, represented here in blue. And once again, it's not obvious from the global adsorption isotherm to see that you have a double Langmuir. But if you do the Langmuir transform, 1 over n is a function of 1 over a, you will see two straight lines at high values of 1 over a. You have this segment, and at small values, you have another linear region which corresponds to the second family of sites. So you can learn something on the nature of the adsorption sites just by these macroscopic adsorptions. So that's good, but it doesn't tell us anything on the reasons why there is adsorption. I said any kind of bonding, right? Good. So I will now spend a few slides to describe the different adsorption mechanisms in the case of adsorption from a solution. First, the reason why you have adsorption may be simply electrostatic interaction. We have seen that some surfaces bear an electric charge, either positive or negative. And if you put them in a solution where you have cations and anions, normally in the solution you have just as many anions in green as cations, but in the vicinity of the surface, here I have supposed that the surface is negatively charged. In the vicinity of the surface, the electrostatic energy of the cations, I'm sorry, here, yes, there is a mistake here. This should be C minus and this should be C plus, okay? So the electrostatic energy of the anions will increase because they will be repelled. They will not be found in the vicinity of the surface. And the electrostatic energy of the cations will decrease, and so they will be concentrated here. So in this region, you will have an excess of positive over negative ions. You will have an accumulation of charge, and you will have a net adsorption of the cations. This region is called the diffuse layer. In fact, the ions in the diffuse layer are not modified in their, I would say, their molecular environment. It's exactly the same as in solution. It's just that they are in an electric potential that is variable, and so their energy changes. That's the first type of adsorption. We may wonder if these adsorption mechanisms result in selectivity, because that's a big problem in the origins of life. You can find a lot of chemical reactions that make interesting molecules. Let's say amino acids, or I don't know, carboxylic acids, but only some of them are used by life. So is there a possibility of selecting them among a huge diversity of related molecules? Therefore, it's important to know if adsorption can bring about selectivity. Well, here, selectivity will only depend on the electric charge. Positive, negative, or more or less positive, that's not very selective indeed. Is it strong adsorption? For typical value of the parameters, it could go to 50 kilojoule per mole. not negligible, but not very strong in terms of values for chemical reactions. Okay, and here, why are the surfaces charged? Here, I will reproduce some of the slides that we have seen a couple of minutes ago. Now we can understand why the clays are negatively charged, for example. You remember, I showed you the structure. I said, if you have substitution of Si4 plus by Al3 plus, there will result a permanent charge located on the structure of the layers. Okay, so therefore they are cation exchangers. In layered double hydroxides, you would have the opposite type of substitution. Mg2 plus would be substituted by Al3 plus. That would mean an additional positive charge. The structure of the layers would not be neutral. It would bear some positive charges, and thus it would be an anion exchanger. And finally, for the case that I have briefly mentioned, minerals that have a pH-dependent charge, that is not a permanent charge, and that includes a lot of interesting minerals like alumina, or silica, or titania, all three of which we have already encountered. Well, what happens is that the charge is due to acid-base reactions. You simply have some surface groups that are either acidic or basic, or both at the same time. Actually, the simplest and best known model for the origin of surface charge is the one-side 2pK model. You suppose that each surface side can both lose a proton, and that means it behaves like an acid, or gain a proton and then behaves as a base. Each one of these proton exchange reactions would be characterized by a value of the pKa, the acidity constant. So that's a 2 pKa model. You can visualize things like this. S is not necessarily sulfur, it means a surface atom. And this is the reaction in which SOH behaves as a base, because it reacts with the H plus in solution, to give SOH2 plus, okay, with the acidity constant written like this. And this is the case in which SOH behaves like an acid because it loses a proton to the solution, leaving a negative charge this time on the surface with another acidity constant. You can easily demonstrate on this basis. You just have to multiply Ka1 by Ka2, and you will see that there will be a pH, that is a value of the H plus concentration, for which SO minus, the concentration in negative sides, will be equal to the concentration in positive sides. SOH2 plus will be equal to SO minus. This pH is 1/2 of pKa1 plus pKa2, and it's called the point of zero charge. When you are at a more basic pH, then both of these reactions are drawn to the right because you are eliminating protons, and that will destroy the positive charges, and that will make some negative charges. So at basic pH, the surface will be negatively charged. If at the opposite, the pH is inferior to the point of zero charge, then if it means you have a lot of protons, you are bringing in some products of these two reactions, you are drawing the equilibrium to the left, and then you are making positive charges. We see that we will have a positive charge for pH inferior to PZC, and a negative charge when it's superior to PZC. And indeed, these are some experimental data obtained on alumina. The values of the surface charges are not the same depending on the overall ion strength of the solution, but they have a common intersection here corresponding to zero charge. That's the PZC. It's close to 7, so we can say at neutral pH, the charge on alumina will be almost 0. On silicas, on the other hand, the value of the PZC is normally around 3 here. And if you are at pH 7, you will be far on the right of the PZC, you will have a strong negative charge. And on the magnesia, that's the opposite situation. You have a high PZC, and therefore, at the same pH, you will have a positive electric charge. Okay. Now, to come back to what I had shown you previously, remember you had seen these two pictures. They correspond to different exposed planes of alumina. And you will have different surface groups here. Some of them will have a high pKa1, some will have a low pKa1. Here, for example, we have the 1A type surface groups that have a low pKa1, so they will be, that have a high value of pKa1, so they will be positively charged at neutral pH. These will be almost neutral. We are too far from the pKa for this particular type of surface groups. Globally, this particular surface, this particular type of phase will bear a positive charge. On the other hand, if you are at a pH that is strongly basic, first these will be deprotonated to give you some neutral OH, and then finally these will be deprotonated, but then giving you some O- groups, and so you will have a negative charge. And we had seen that surface groups on the 1,1,1 phase had a different acido-basic behavior. The OH groups here, because of the strong withdrawing effect of the 3 aluminum ions, have a strong acidity. They will deprotonate at a very low pH value. They will give you a surface that is negatively charged. So we can find a region of pH in which the first surface is positive and the second one is negative. The same particle can exhibit at the same times positively charged and negatively charged faces. Okay, but electrostatic adsorption is not the only adsorption mechanism. First, electrochemists soon realized that in some situations, the ions could be adsorbed by some kind of specific adsorption. They didn't know what it was. They just modeled it by adding a second type of adsorption in which the cations here, we are still in the vicinity of a negatively charged surface. The cations are held by something that maintains them at a fixed distance from the surface. That is called the Stern layer, or the layer of specifically adsorbed ions. The sum of the surface charge plus the Stern layer charge can be either positive or negative, and then you will have a diffuse layer. That's why this is called the triple layer model. But what is the nature of this specific adsorption? Well, it's probably not the formation of covalent bond. It's probably something like H bonding. It's very difficult actually to characterize due to the lack of good techniques to see ions in buried interfaces, in the interface between a solid and a water phase, a water solution. But we can call that an autosphere complex. Autosphere because a particular ion, for example, will not lose its ligand, its coordination sphere. It will welcome some groups from the surface, as, for example, OH able to give H bonds in the following layers, in the hydration layers. That would be the outer sphere as opposed to the inner sphere that contains the ligand. And that would be very interesting if we know that surfaces can make specific H bonds with organic molecules, for example. There would be many connections with biochemistry. You know, of course, the role that H bonding plays in the recognition of the base pairs in DNA. In the same way, hydrogen bonds also contribute a lot to molecular recognition in the active sites of enzymes. So if we can have specific layers of H bonding on surfaces, maybe we could have the beginning of a kind of biochemistry. We could have some specificity and even some kind of molecular recognition. On the other hand, you could say, well, this is not strong adsorption because an H bond, this is weak. But if you have several H bonds, the joint effect, the additive effect of all these bonds may be indeed quite strong. Yes, I will go quickly over this. Just to tell you that we know something is happening between the adsorbed molecule, the surface, but water also plays a role. And if we want to give a complete description, we have to take into account the hydration of the adsorbed molecule, of the surface site, and of the complex between the two. Right? That's what complicates a lot estimates of the energetics of this kind of stern layer or specific adsorption. And finally, adsorption can also involve the formation of inner sphere complexes. Inner sphere complexes means covalent bonding, means that the surface groups have formed a simple covalent bond with one of the atoms of the molecule that's being adsorbed. Imagine, for example, that you have this SiOH on the surface of silica, and you have an acid that comes near, COOH. The two can react together to form COOSi, sometimes called surface ester, and eliminate one water molecule. All right? Coordinative bonding is a special case in which you have a bond between a ligand and a metal ion. And to give you a relevant example for prebiotic chemistry, alanine, which is a simple amino acids, on silica makes a specific type of bond that translates in NMR by a strong displacement of the chemical shift, which we interpret as saying that the COOH of alanine, probably deprotonated, has formed a coordinative bond with a Ti4+ of titania. So that's an example of inner sphere complex formation. That would, of course, grant some strong chemical selectivity. You cannot react a surface group with just anything. You need to have the right kind of moiety on the adsorbing molecule. That would also give you a probably much stronger adsorption, although when you look at real instances, maybe it's not so strong, but certainly it could reach 100 kilojoule per mole. And because life is always complicated, sometimes you have two adsorption mechanisms at the same time in the same system. I will take an example here from a classical coordination chemistry study, the adsorption of glutamate, another amino acid, titania from water. And what you see here is strong adsorption at acidic pH, falls to zero almost at the point of zero charge of titania. That's easy to interpret. Glutamate is a negatively charged molecule. Titania is one of those oxides with a PZC. And remember, it's positively charged under the PZC. So we have a positive surface, a negative molecule. They attract each other. You have electrostatic bonding. Above the PZC, both the surface and the molecule are negative. They will repel each other. And consequently, you have no adsorption. But if you add some calcium to the solution, then you get a very different shape of the adsorption data. It starts almost in the same way, but above pH 7, we have, again, an upshoot in the adsorption. What happens there that was not possible without calcium? Most probably it was the formation of a three-partner adduct. You have a negative surface, you have positive calcium, okay, it will go into the stern layer, making a specific bond with the surface, and the calcium will be able to make a coordinative bond with a glutamate. So you have a three-partner adduct, and therefore you have an increase in adsorption again. And this was treated quantitatively, okay? They wrote the chemical reactions, they wrote the equilibrium constants, and they were able indeed to justify, you see, that's the theoretical fit here. It fits quite well with their data. Finally, just to show you that the structuring of the surfaces that I showed you in the beginning can induce some structuring of the adsorbed molecule. This is alanine, an amino acid, adsorbed on copper, observed by scanning tunneling microscopy. You see here the individual alanine molecules. They are indeed periodically disposed, and not only that, but they make chiral adducts, which indeed is very interesting from the prebiotic chemistry point of view. So this was seen by scanning tunneling microscopy, and also by a technique that I did not have the time to describe to you, which is a kind of surface diffraction, low energy electron diffraction. Now, this is interesting, yes, but first it's on a metal, native metal, not so prebiotic, and also the conditions. If you want to apply STM and lead, not only you need a conducting surface, but you also need a high vacuum. You need, and that's why these techniques are very expensive, you need a vacuum of 10 to the minus 10 torr, or millimeters of mercury. Is it realistic prebiotically? Well, not on the Earth, but most probably in outer space. So it would be relevant in the field of electrochemistry. Okay, now some words about heterogeneous catalysis. And I think that's important because these are very simple, chemical concepts. In principle, everybody learns them, but it appears when you have to apply them to a new situation, also many people don't remember these basics. So how can you know if a chemical reaction is possible? First, the first criterion is the thermodynamics. That's the delta G0 that I have mentioned already. I've mentioned it for adsorption, but it's a general fact of life that a reaction will be possible if G0 decreases, if delta G0 is negative. And that's very simple. If you have A turns into B, for example, well, thermodynamicians have made extensive tables. Just look up the G0 of the product and the reactive, calculate the difference. If it's negative, okay, you can try. If it's positive, you can forget about it, and no matter if you add a catalyst, it will not work. At least not in the conditions for which the G0 values were determined. So you must find another scenario. And only then you can investigate the kinetics. Many reactions are favored, are thermodynamically possible, but they don't happen at a measurable scale because they are too slow. Then you have two solutions. Either you heat, you will speed up all reactions, or you use a catalyst, okay? So a catalyst, by definition, is something that speeds up a reaction, but doesn't appear either as a reagent or as a product in the global reaction equation. And that means that because it still has to interact with the reagents at some time, that means that in technical parlance, the sequence of reaction steps will be a closed sequence. And a closed sequence is something that can be written as a cycle. Let's look at an example. A is transformed into the products P over a catalyst C. So globally, A turns to P, C doesn't appear. And a very simple sequence of elementary steps will be this one. First, A binds to C to make some intermediate AC, and then AC releases the catalyst and at the same time causes the transformation into product P. If we make the sum of these two steps, C disappears. That's what is called a closed sequence. But then we can write it like this. First step would be this one, and second step would be this one. We are seeing things from the point of view of the catalysts. It cycles between C and AC. At each turn of the cycle, 1A is transformed into 1P. So that's catalysis from the kinetical point of view of the kinetical description. But why does it make the reaction faster? Well, then we need to look at things not really on the thermodynamic level, but on the level of the single molecule. Let's write a vertical scale of free energy. And here we have a reaction, reagents to products with a negative delta G0, the products are lower. So the reaction is thermodynamically allowed, that's the first point. But between the reagents and the products, some things happen, some transformations along a reaction coordinate. I don't know which one it is, but at some intermediate time, it will cause an increase in the free energy. You have an energy barrier here. And the height of this energy barrier is the free enthalpy of activation, noted with this exponent, the difference sign. And you have something that looks very much like the expression for the thermodynamic constant, but this time it's an expression for the kinetic constant K, related to the reaction rate. K is exponentially, in an exponential decreasing proportionality with delta G of activation. That simply means the higher the activation barrier, the slower the reaction goes. And now, why does the catalyst work? Simply because it will provide another reaction path here, which has a lower activation energy, delta G of activation, in the presence of the catalyst is smaller, and according to this reaction, K will be higher and the kinetics will be more favorable. From the industrial point of view, from the practical point of view, a catalyst may be defined in terms of its activity and its selectivity. The activity depends on how fast the reaction is going. So we have just seen what it means in scientific terms. It depends on the height of the energy barrier here. But the selectivity is very important. And I'll give you just one example in the industry. You can want to oxidize a propene. There could be many different outcomes in the reaction between propene and oxygen. You only want one of them, so you want to open selectively one of the transformation channels and not the others. Here, we have a small activation energy with respect to the transformation that is shown, and there might be other products with the same reagents that are lower on the G0 scale. They would be more favored energetically, but because the activation barrier here is higher, this is kinetically hindered. And then you can have a strong selectivity even for the product that is not thermodynamically favored. An example in biochemistry, of course, is the case of enzymes. Enzymes have an exquisite selectivity. They are also very active, okay? And so they master these two parameters. But, of course, at the origins of life, there were no enzymes. On the other hand, and in comparison, in the chemical industry, you use very often minerals, so inorganic surfaces, because things happen at the interface. And these usually have a moderate activity and a rather coarse selectivity, right? So what we are going to do when we study the origins of life is to see, can a given enzyme be replaced by a particular surface? Now there is another general principle from catalysis that is useful to remember. It's Sabastier's principle. It's, in other words, the Goldilocks rule. The best catalyst will be the one with the optimal energy of interaction with the reagents, not the highest possible one. Let's compare these three situations. Here you would have a reaction in the presence either of no catalyst or of a bad catalyst with a very small interaction with the reagents. The activation energy remains high. Here you have reaction in the presence of a catalyst with a moderate affinity for the reagents. It will form some kind of intermediate which is at moderate energy. As a result, the energy barriers here will both be rather low. That's the best possible catalyst. And here, you would have a catalyst with a very strong interaction with the reagents. It would form an intermediate. It would bind to the reagents and be very stabilized energetically. And then the reagents would actually be trapped in this state. There would be a new high energy barrier. The best catalyst is this one. So now, this was in general what is catalysis. Now, what is heterogeneous catalysis? Well, that's heterogeneous refers to the existence of two phases. That's when the catalyst is in a different phase from the reagents. Most often, you have a situation where the catalyst is a solid, and especially a mineral species. And the reagents are either in the gas phase or in the liquid phase in solution. So that's something that is very important in our society, and there are many labs that study heterogeneous catalysis. And that's also a possibility whenever mineral surfaces are present, just like at the origins of the Earth. Remember our scheme of the beginning, when you had minerals on the islands in the presence of reactive organic molecules in the solution. In the case of a heterogeneous catalyst, you also have a catalytic cycle, but now the catalyst is a reaction site. Yes, once again, our little star. This is a very simple cycle in which A is somehow activated by its interaction with the reactive site. This would be the adsorption. And in the second step, A is transformed into P and the catalyst is regenerated. And now we can fit all of it together. For example, we can write a catalytic mechanism like this in 2 steps. That would be the simplest possible heterogeneous catalysis mechanism. A from the liquid phase reacts with the site to give the adsorbed molecule, and in the second step, the adsorbed molecules transform to give P and regenerate the free site. If you want to treat it in the frame of kinetics, you must make some approximations or some hypothesis. Suppose that this is the rate determining step, the slow step, and this one is much faster, so we can believe that it's in a kind of equilibrium. But then we know how to treat this equilibrium, for example, with the Lambert model. It's just adsorption. So it's very easy to write a kinetic rate equation. According to this step, the kinetics will just be proportional to the concentration in adsorbed A species. And there will be a kinetic constant here. But we can get this from our Lambert model of adsorption. Right? We can substitute this value of the concentration of adsorbed sites into the rate equation, and we find that we have very similar to the Lambert isotherm, but this time to find the reaction rate, the kinetics of the reaction. For example, we can say this reaction will proceed faster if we increase the concentration of A, but only to a given amount, because it happens on the surface sites, and when they are saturated, then the reaction cannot go faster. So we will have a plateau here for some value. Okay? And that's what the specialists of heterogeneous catalysis used to do in the beginning of their science. And of course, they complicated these models. I don't want to go too much into the details, but this is a model that's very often employed, the Langmuir-Hinshelwood model, for a reaction with 2 partners. A plus B gives some product P in the presence of a heterogeneous catalyst, that is, in the presence of reaction sites. Well, this is an image of what happens on the surface. Some molecules of each are adsorbed, and when they are close together, they will give you the product. Well, you can write this in terms of elementary steps: 2 adsorptions, both at equilibrium, and a rate determining step between the 2 adsorbed molecules. Okay, then there will be a little mathematics and another, a little more complicated expression for the reaction rate as a function of the activity of A and B. And I will not show you, but it will look like this. If you change the reaction, if you change the concentration of A without modifying any of the other parameters, then you will get something like this. It starts by increasing, there is a maximum, and then it decreases. Okay, so you can have some complicated behaviors, and the industrialists, of course, wanted to understand that in order to optimize the conditions for reaction. So that's how people used to treat heterogeneous catalysis. Of course, when they became able to recognize adsorption sites at the molecular level, they could also recognize reaction sites. And I could give you many examples of this identification of reaction sites. But now let's just say very quickly, what can heterogeneous catalysis do for you? How can it be used, for example, for prebiotic chemistry? Well, first, heterogeneous catalysts can build CC bonds. And that's very interesting because you want to make long molecules from short ones. You have to build a skeleton, carbon skeleton. You have to make CC bonds. Well-known example is Fischer-Tropsch chemistry. When you work from synthesis gas, CO plus H2, in these particular conditions, well, you can have the buildup of long hydrocarbons, chains of CH2 and CH3. How does it happen? Well, you have some complicated mechanisms that have been proposed, and they go like this, but they happen on the surface. You have some CH here reacting with adsorbed C, and here you see you have made a CC bond. This would be a step on a metal surface. This would be a well-defined reaction site. Now, Fischer-Tropsch chemistry is used to make synthetic oil from synthetic gas that can be obtained from coal. But it's also invoked in astrochemistry, as you may know, to explain the existence of the first long carbon molecules. Another way to make carbon skeletons would be to use Bronsted acidic activation of molecules such as alcohols. And it's used, for example, in the MTH reaction, methanol to hydrocarbons, that is carried out on zeolites. That's interesting because it's also one case in which autocatalysis has been reported. Autocatalysis is a phenomenon that is often investigated in origins of life studies. Because the initial formation of hydrocarbons is slow, you see it goes like this. Methanol molecules lose water to give some alkenes, and you have a kind of catalytic cycle in which the catalyst would be indeed an olefin. In the beginning, you had no olefin, and therefore you had a very slow reaction, but the product of the reaction, that is eliminated here, is one olefin. The reaction produces its own catalyst, so the reaction will speed up almost explosively. What are the reaction sites in this case? So what can you invoke as reaction sites if you want to build skeletons using this chemistry? You need very strong Bronsted acidic centers to promote hydration and dehydration reactions. And in particular, these ones would be very efficient. These would be SiO Al sites in a zeolite lattice. In a zeolite lattice, a few of the sites are aluminum 3 substituting Si, and the charge deficit, 3 instead of 4, has to be compensated. It can be compensated by a proton. It gives you a very strong acidic site. Another thing that heterogeneous catalysts are very good at doing is selective oxidations. Now, in this case, heterogeneous catalysis can be very selective. I'll give you an example here, and it's a transformation of propene or propane in the presence of O2. And here are some of the possible outcomes of these reactions on the G0 scale. You see there are very many of them, and that's a situation in which you can wonder about the selectivity of the catalyst. Is it possible to open one pathway, let's say from propene to, I don't know, here, this would be acetic acid. If you want acetic acid, you can you do that at the exclusion of all others? And indeed, that's possible with the same set of reagents using different catalysts here in green. You see that you can obtain selectively very different outcomes. This one is complete oxidation, it's not interesting. But some of them are quite interesting. Here, for example, you have acrolein that is used in the polymer industry business. Some of these reactions can be carried out with a selectivity of 96 to 99%. That's very attractive. Okay. I think I will go over the first following examples quickly. Just show you this small example of a molecular level characterization of catalysts to see what can be done now. And here we see again an example of STM microscopy. That's a complex oxide that is used for the amoxidation of propene, and the reactive site was identified both from kinetics and from this type of molecular level surface characterization. So we start to have a very complex chemistry that is completely mastered. And here, of course, you don't have time to understand. The message is that's a very complicated catalytic set of reactions. And each step has been identified on the surface at the molecular level. All right. You can also make selective reductions. But if I want to conclude on this part, which has been a little too long maybe, but the interest of heterogeneous catalysis is that we have the results of a long characterization for decades, both at the macroscopic kinetic level and now at the molecular level of the reactivity of surfaces. And we also have some advanced engineering of the reactors to carry out these heterogeneous catalytic reactions. So that could be used with a lot of profit in the OOL literature. Of course, you could say that the reactions are carried out in conditions that are not very prebiotic. If you had time to note some of the conditions, like 200 degrees, 100 atmospheres, that doesn't look like what could have happened on the early Earth at any time. But now, and more recently, green chemistry has known a lot of developments. And green chemistry means that you are trying to carry out heterogeneous catalytic reactions in milder conditions. So the conditions are converging with those of the origins of life. And there is a lot of potential to use the concepts and the results of heterogeneous catalysis. And so now, in the last part of my talk, I will give you a few examples of scenarios where minerals have been invoked in origins of life. The first one is to explain confinement. What does it mean? Well, why is confinement necessary for life? Well, because dilution is death, and dilution is favored thermodynamically. Okay, because of this thermodynamic equation, but I don't have to go into the details. I just have to carry out a simple experiment. I take a beaker full of water, and I just drop a drop of ink, and you know what happens. After some time, ink will be distributed over the whole solution. That's the thermodynamic outcome. So even if you had some interesting chemistry that was a precursor of life, there had to be something to keep it in the same place, or otherwise it would have been diluted to death. And one possibility is that confinement could have been ensured by adsorption. Adsorption concentrates molecules in the vicinity of the surface. For example, electrostatic adsorption will keep an excess, let's say, of cations in the vicinity of the surface. And that's stable thermodynamically. They will not go away. Okay? So some people said maybe life started in the vicinity of surfaces. Maybe at the origin we had two-dimensional life, like flat organisms. And variation on this hypothesis is the so-called soup and sandwich model. Soup for the primordial soup, and sandwich, well, because some people like Helen Hansma, mostly, have proposed that the reactions of life started between clay layers. What you have here is a small crystal of clay. The green slabs are the clay layers. Each one is 1 nanometer thick, and they can be separated from each other, as I told you. You can swell the interlayer region. And here, this is, it's just a cartoon, a view of what could have happened. In some of these interlayers, you had some chemistry conductive to the formation of nucleic acids. In others, you had some chemistry conducing to the production of proteins. And here, what you see is that these systems are slowly being carried and taken away by a different means of confinement, of compartmentalization. That is the formation of bilayers, of lipid bilayers, which of course are what hold the current cells together. The cell is limited by a bilayer, that's the outer membrane, and that's what prevents it from being diluted. So life started as a sandwich here, and then there was a transition that allowed the formation of lipid bilayers, and this chemistry could be liberated, freed from the surface. Okay, so one of the components of this model, and that would be the second hypothesis, is that clays somehow have transmitted or their confining capabilities to another system, to the lipid bilayers. And this has actually been empirically tested in a paper co-signed by Shostak, who was also a Nobel Prize. He tried to make fatty acid micelles, so he needed a high concentration of fatty acids in the first place, and in some conditions they will be transformed into vesicles, okay? Vesicles that contain a small amount of water. And he did that both without and with montmorillonite, which is a special clay. And you see the result here. With montmorillonite, it happens much faster. In addition, he also observed the formation of these vesicles by fluorescence techniques, and in some of these vesicles, he actually observed some small pieces of clay, indicating that indeed the last step of the soup and sandwich model could be viable. This is the reference. Main author is Hanchitz, and that's a very much cited paper. Another rather general application of surface science, in this case of adsorption, is to solve the question of enantioselectivity. And I suppose that you know what I'm talking about. Life makes use of, for example, amino acids These are chiral molecules. They have two enantiomers that can be called left-handed and right-handed, but only the L form is being used in proteins. We have almost 100% selectivity. Actually, the other form is very toxic. And still, the two enantiomers have exactly the same energy. So how could one of them be selected at the origins of life? There are many answers to this question. One of them calls upon adsorption, and it has also been tested experimentally, so that's just not just an idea up in the air. Okay? Well, we have to understand first that some surfaces are also chiral, in the basic meaning that they are not superimposable to their mirror image. That happens on calcite, and, well, here you have the different atoms of calcite, calcium, carbon, and oxygen in different colors, and you see that the patterns that are drawn by identical atoms here are chiral because the mirror image with the side bones, if you want, on the right, the mirror image would be with the bones on the left, and it's not superimposable to this type of, to this particular image. So we have a chiral surface. And therefore, it was quite logical to say if the surface is chiral, if it's interacting with a racemic mixture of amino acids in which you have the two forms in equal concentrations, maybe the surface will not interact in the same way. And that's what was tested by Bob Hazen. He checked on a surface with a given chirality. He checked that D-aspartic acid adsorbed more strongly than L-aspartic acid by a value that is not negligible at all. So he put his mixture of the two enantiomers, and after adsorption, the D enantiomer was retained on the surface, and the solution was enriched in the L enantiomer. Okay. There are several other domains in the origins of life business in which mineral surfaces have been invoked. My next one will concern the first transition that belongs to chemistry, making small molecules from atoms. Well, actually, that's not very new. Using, in particular, heterogeneous catalysis to explain the reactions of astrochemistry, the appearance of the first organic molecules in the protostellar nebula, well, this is something that is done by very many teams. So astrochemistry makes large use of the notions of heterogeneous catalysis in order to make first some small molecules like this, acetaldehyde, or simply a carbon monoxide, and from these to go to more complicated things like amino acids, nucleobases, and sugars. They are made in meteorites. We have detected them, although in rather small amounts usually. So we have to understand the chemistry that starts from these small precursors and goes to the first biomolecules. And as I told you, many teams are doing that and making good use of the methods of heterogeneous catalysis. The next step is going from small molecules to macromolecules. molecules like proteins and nucleic acids are one-dimensional polymers, like a string of pearls in a necklace. In particular, if you want to make a protein from 2 amino acids, so you have to start with the first 2, right? What you want to do is to make a peptide bond. The COH of one amino acid will react with the NH2 of another one to make this CONH, the peptide bond, while releasing one H2O. And if you repeat it at the ends of this growing chain, you can get a very long amino acid chain, you can get a very long peptide. Now, as usual, we have to check the thermodynamics first to see if it's possible. And here I will give you as an example the reaction between glutamic acid and leucine, 2 amino acids that I have studied quite a lot. This is what thermodynamics says. If I want to make the dimer, GLU, from the separate amino acids, I just check their molar free energies, and this is the delta G0. You see, it's positive, although not by a lot, and that means that this reaction will be disfavored. Maybe a few molecules will react, but the vast majority will not. I will stay with the monomers. Okay, that may be a question of concentration. If you dig deeper into the thermodynamics, the driving force is not exactly the delta G0. It's given, as people who have done some biological thermodynamics will know, by this formula it depends on delta G0 and this, which is a ratio of the concentrations. So maybe if I work with the different concentrations, closer to reality, that will improve things. So delta G0 is defined for all species at the 1 molar concentration. What if I take the millimolar level? Well, I can just apply the equation that I have shown you, and well, you see what I get. Now it's plus 25. It's even more positive, so it's worse. And that means I'm not going to succeed in condensating 2 amino acids in solution. No way to do it. But we know, it has been checked since the 70s, that if you deposit it on some minerals like silica or clay minerals, and you heat a little bit, then you will get some peptides. Why? Well, to cut a long story short, and I will speak in more detail about it at the French Medical School on the Origins of Life, the main reason is to be found here. In the reaction, you remove 1 water molecule. And if you remember Le Chatelier's principle, if I remove one of the products, I will drag the reaction equilibrium to the right. So if I keep removing water, I will make the condensation favorable. I will have a high concentration of the dimer at the end. And when I'm heating on a surface, well, I'm drying the surface and water goes away. And so that explains why it becomes possible. Can it really be used to explain how peptides came to be? First, can it make long peptides? Well, I think that the best result so far in one step is to go to 8 or 9 monomer long peptides. And they would not be the majority species too. But if you apply successive wetting and drying cycles, for reasons that are slightly more complicated, you can improve things. So we believe that indeed this scenario can be used to make peptides long enough to be useful, to carry out something useful. And then there is a question of sequence selectivity, because you don't want to make just any peptide. You want to make, let's say, a molecule that can be used as an enzyme, and then it must have a very precise sequence of amino acid. And to understand how likely it is, well, you can view the primordial soup containing different amino acids, like an alphabet soup, and imagine that you take one spoonful at random. How likely do you think it is that you would find this? Not very much. And you can make the calculation, and indeed it's extremely unlikely to have any kind of selectivity for the synthesis of peptides, unless you have a preferential interaction with the surface, unless you have some selectivity in the adsorption. And indeed, we have investigated it and found at least some selectivity, not like that perhaps, but there are some channels in which polymerization seems to go. Some sequences of amino acids are flavored above others because of the details of the interaction with the surface. And the last big example of application of mineral surfaces to OOL is in the appearance of metabolism. Metabolism involves both small molecules and macromolecules to make functional systems. So, what is metabolism? Well, it's something that is very complicated, and I can illustrate it. Well, this is a chart that is sold and illustrates only the central pathways of metabolism. Okay, if I zoom in even to a small part, you see this is the so-called inverse tricarboxylic acid cycle. It's still very complicated. My general definition could be that metabolism is an integrated set or a network of chemical reactions which happen under some kind of central regulation. So there is no purpose, of course, in the origins of life, but there is still some kind of a cybernetic control. Can that happen? It doesn't happen naturally in chemistry. You will not find reactions self-organizing like this easily. Well, some people have proposed that at least some of the pathways of metabolism could be duplicated by non-biological chemistry, and especially using surfaces. One researcher who had a lot of success some 30 years ago was called Günther Wächter-Seuser. He was a scientist working only on paper. He was employed at the Office of Patents, like Einstein. And he just wrote some sets of synthesis pathways that could more or less do the same kind of things as current pathways of biological metabolism. Here it's maybe hard to see the surface, it's here. He used iron sulfides, and he used it actually as a reagent and not as a catalyst here. Anyway, that interested people a lot at the time because it provided at least possible ways in which metabolic reactions would have come to exist. But as I said, it was chemistry on paper, and sometimes the surface chemistry was not right. He used, for example, a model in which the iron sulfide particles had to be positively charged, while experimentally they are negatively charged. So it was only very partially confirmed. More recently, there are other people who have tried again to address this question in a more systematic way and to reproduce some pathways of metabolism. Now, for example, let's ask how you can make a nucleotide. There has been extensive work by John Sutherland And he proposed some very clever sets of chemical reactions, which you can see here. You don't have time to identify all of them, but you can see that the starting reagents are, let's say, reasonable small molecular precursors here, like nitriles or like small alcohols, which have been known to occur in astrochemical reactions. And after some really possible, tested experimentally reactions, he obtains something at the end that is not really a nucleotide, because this is not a regular base, but that looks like a nucleotide. Okay, but all of the individual steps are different from those of biochemistry. And so there are two problems in there. First, the first one is that in order to make all of these reactions, you need human intervention. You need at some time a separation of the reagents from the products. And there were no chemists in white lab gowns at the origins of life. The second problem, that's a philosophical problem, it's called Occam's razor. And in Latin, it goes like that. Ensia non sunt multiplicanda praeter necessitatem. You should not multiply entities beyond necessity. If you are trying to explain something, you should keep the number of gratuitous supposition at the minimum, okay? And that means, as applied to the problem at hand, that if we have a given complicated network of reactions that produces a nucleotide in today's biochemistry, it's more economical to say that it's an adaptation of something that was already similar than to say that we started from a very different network of reaction, and then at some time life had to invent another completely different way of making the same thing. And that's why this is definitely not something that has to be seen as a general principle. I know that some people are very much against this idea, but I believe that at least it's good as a research program. It's called the geochemical continuity hypothesis. And that means, let's take some relevant parts of metabolism, a sequence of reactions, or even better, a cycle that would be very typical of metabolism. And let's try to reproduce it. But it's forbidden to use the things that are part of today's biochemistry and that didn't exist at the time. No enzymes and no biochemical components like ATP to provide energy. You have to find a different way. For example, you have to substitute enzymes with mineral catalysts. And one team that's been doing that a lot is the team of Joseph Moran, who used to be working at Strasbourg, and he spent a lot of time trying to reproduce the reverse tricarboxylic acid cycle, the one that I have shown you on the metabolic chart. It would be interesting because you see, if you run it in this way, well, you will take in some CO2 here, and you will form some more complex molecules. That's a way of fixing CO2. And he didn't succeed in reproducing the cycle in itself, but yet he could duplicate several key steps by reflecting on the kind of chemistry and using, in many cases, the appropriate mineral to catalyze the concerned step. Another example, this one from my team, and it relates to the synthesis not really of nucleotic acids, but at least of one of their key parts, the nucleobase. We have something in current biochemistry that is called the orotate pathway. That's how cells will make the pyrimidine nucleotides, cytidine and uridine monophosphate. They start from a simpler molecule, an amino acid, bicarbonate, which is inorganic, and by a sequence of reaction, they will reach the formation of the nucleotide. The key part, the formation of the base, occurs until here. The green circles are the enzymes that should be substituted, and there are also some places in which there is an energy input here, and also here, in which ATP is degraded. And Louis Thérault-Vanessian, who was a PhD with Marie-Christine Morel and myself, has indeed succeeded in reproducing some key steps of this reaction cycle. Now, the first step, condensation, it should be with something called the carbamoyl phosphate, but that didn't work. It had to be substituted with a CNO minus cyanate, which is indeed a likely prebiotic precursor. Condensing it with the aspartic acid to give NCA is not so difficult, actually. This one is thermodynamically favored. It doesn't even need a catalyst. The next one is another condensation to make a cyclic structure. That's also a condensation. And we knew that we had silica that could condense amino acids. So we said, why not use it as a catalyst to make, well, this particular molecule, which is called DHOA, since it's also a condensation reaction. Here, in the biochemical pathway, there is the input of chemical energy in the form of ATP. Instead, we use a drying step, just like we did for the amino acids. And instead of the enzyme, we used SiO2 as a mineral catalyst. And we succeeded in making a cycle. Unfortunately, it's not exactly the same cycle. It's a 5 cycle instead of a 6 cycle, right? So the next step, the oxidation, we could still come back to the main cycle by a kind of isomerization. What that means is, in this case, we have tried the hypothesis of biochemical continuity, and we got an answer. You know, is it falsified or is it confirmed? Well, for example, we could not use the same precursor, but we had a slight variant of this reaction sequence that was still quite likely. And here, it worked, but not exactly in the same way. So we proposed a different pathway to go to the final nucleobase. And so you see that the research program was successful indeed, because trying to reproduce metabolism, we didn't exactly succeed, but we could still propose a likely pathway to the final molecule. Yes. We'll not go any further, yes. Another point that was interesting in this thesis was the analogy between the biological catalyst of today and some of the mineral catalysts that were proposed instead. This is the reactive site in dihydroorotase, the molecule, the enzyme that synthesizes one of the intermediate products, the cycle dihydroorotate. You see that there is a central cavity with several amino acids, and in particular, there are 2 zinc ions here. This is a closer view of the reactive cycle with the 2 zinc ions and a bridging OH group and interacting with the final product, dihydroorotate. Now, the catalyst that Louis Thérault-Vanessian proposed was a zinc exchange zeolite, in which this is the zeolite framework. It has compensating cations, and they could be replaced by 2 zinc ions. And it's possible, indeed, to have a Zn-OH, Zn complex, just like here. So you see that even though it's a mineral catalyst, it does resemble the enzyme in some way. That's also an interesting research avenue. Okay, I don't have time to tell you about this, although it would be interesting. And I will finish my talk with something that is more of a provocative opinion than a really serious idea in my view. It's already quite old. It was developed by Karen Smith, who doesn't live anymore now, in his book, 7 Clues to the Origins of Life. In fact, his idea was quite radical. He said, you think that clays may have catalyzed the formation of the first molecules of life. Well, I say that clays are the first living beings. And he explained, one of the characteristics of life is that it holds information, in particular in a linear sequence of nucleobases in DNA, like A, G, T, C, and so on. And he said, well, I'm a mineralogist, and I know that clays can also hold linear information. Now, in detail, it would be complicated to explain, but there are slight differences in chemical composition and also crystallographic orientation that makes that there are indeed different types of clay layers. Just to illustrate it, I have represented them as orange, green, brown, and blue. So we have a sequence of clay layers, which is an informational sequence. Then he said, living beings can grow. Well, clay crystals can grow too. Then life can reproduce. Clay crystals could also reproduce simply by breaking fragmentation. And if you break this large crystallite into smaller ones, they still hold the same sequence of layers. Information is conserved. And he even said that there could be some Darwinian evolution. Okay, some of these sequences, clays, they will grow in hydrothermal environments, but some of these sequences could grow faster than others. This is taken from an internet site, and let's suppose that originally you have this particular sequence that gives rise to a clay, that's a clay genotype that gives rise to a phenotype that grows slowly. And at some time there is a mutation. For some reason, while growing, the sequence is not correctly copied. And the new sequence is actually able to grow faster. It's represented here as the pointed crystal. And after some time, it will displace and even eat out the first type of geotype. And we can say that one type of clay genome will have been selected over another. And maybe this is the most dubious part of the scenario. He said, does it have a relation to today's life? Well, it may be that at some time there was adsorption for the prebiotic soup containing all of the right nucleotides here. And we had our living clay. And it just happened that the different types of layers had different affinities for the nucleotides. Like the orange one will prefer to adsorb A, the brown one will prefer to adsorb G, and so on and so on. And since nucleotides on the clay crystals are also known to polymerize, just like amino acids, he said, after polymerization, I will get, I will get a sequence of nucleic acid that will mirror the sequence of layers in the clay crystal. We will have a translation from the mineral to the biological world. Well, in fact, I don't know if I have written this sometime. Yeah. This is very interesting conceptually. It helps you to think outside the box, but most of this is, once again, just chemistry on paper. There have been very few attempts at testing parts of these hypotheses, and the results are not conclusive. But still, there is a question that is very important. Can surfaces, or can minerals in general, encode information? Could there be, for example, one-dimensional information in clays? Well, there are spectacular photographs. This is a stack of kaolinite layers. It looks like a book. We could say that's the book of life, but that's good for popular science. When you try to test it, well, there have been very partial, let's say, hints going in this direction. So, like, for example, this team has tried to grow some saponite crystals, and we know that the saponite has some swelling and non-swelling regions. You can reveal the chemical differences by intercalating a given type of molecules. Some of the layers will swell, and some of the layers will not swell. And it's very easy to see by electron microscopy. And so they could follow the reproduction of information, the succession of swelling and non-swelling layers by successive electron micrographs. Okay, but that's a very limited test. In addition, there is also another possibility that surfaces, when they are two-dimensional, and the information they encode could also be in two dimensions. And people who are very specialized in this kind of study have, for example, evidenced some clustering in the central sheet of a clay layer here. You have the octahedra. They can contain different ions, and they do not distribute randomly. You can say that you have some information that distinguishes between different clay minerals, but it's two-dimensional information. And we really do not know very much, or maybe nothing at all, about how such a type of information could be used and certainly could be transformed into one-dimensional information. So, to conclude, well, what we know is that sometime we had chemistry that turned into biochemistry, into biology, by a process of complexification, because we are here, right? And we have to find out how this happened, because it's one of the basic problems in current science, and also for applied reasons. If we understand how complexity came to be, maybe we could exploit it to make more complicated devices. We know that it happened on this Earth, and that there was already a complex mineral world in existence before the beginnings of biochemistry. I have given you a few examples of how surfaces can be complicated. And therefore, there are very many opportunities for surface reactions in origin of life research. And once again, I have very briefly summarized one of the few research directions that are exploited now. But we are not yet very far. We need more experimental investigations. There are very interesting theoretical propositions, not enough experimental tests, although I would say that in the last 10 years, the situation has improved. Okay, so we need more experimental research. And in particular, we need, I think, more interaction with people from surface science, heterogeneous catalysis, and the study of adsorption reaction. And of course, here, I'm preaching for my church, as we say in French, because that's just where I came from. Okay, thank you for your attention. This will be all. I don't know if you have time.
Thank you, Doctor. Thank you, Dr. Lambert. Any questions? ¿Alguien tiene alguna pregunta o comentario?
First, thank you for the presentation. It was very interesting. And I have one technical question about these dry wet cycles, because I want to work with the oligomerization of the amino acids, but I'm stuck with the problem of what technique can I use to analyze or search for these oligomers, because I want to use HPLC, but with this technique I'm rehydrating.
Yes, indeed, if we want to make progress in this type of question, we need good analytical techniques. We studied it in the case of glutamic acid plus leucine, mostly by advanced mass spectrometry. But it takes a lot of time, and we wanted to analyze trimers. If you take trimers with two possible amino acids, that already makes 8 different chains, and distinguishing them by mass spectrometry is time-consuming, is possible, but it really takes a lot of patience. You mentioned HPLC, that's fine, if you have some reference compounds in order to identify the different peaks. But I would say that we are making a lot of progress lately to apply some advanced like artificial intelligence approaches when you have a huge amount of data, like the mass spectra of a large number of solutions. And probably we'll be able to make much faster progress. But we still need the hardware. We need the mass spectrometers. It was FTICR, and that costs a lot of money.
Thank
you.
So
it's not necessarily cheap research unless you work on very simple model systems.
¿Alguien más quiere?
Also, thank you very much for the talk. It was very illustrative and also very dense, information dense. And well, my question is in regards of the computational simulations and in silico experiments, as some call them. And we have at the moment in our work group 2 possible approaches for the simulation. One is the geochemical simulation with programs such as Minicurso and CD Music. And on the other hand, we have the more quantic and bioorganic, like bioinformatic approximation that tracks the 3D coordinates of the atoms and the bonds. But we seem to be stuck on both ends because none of them are mixed enough. One is too bioorganic and like biochemistry, and the other is too inorganic. So in the case of the simulations and the computational approximation, which tools are most effective to avoid these kind of shortcomings of the state-of-the-art simulation process?
Well, that's a big question. I think the first one, you were talking about modeling adsorption reactions by geochemical approaches. So that's what I call the classical approach to adsorption. And it gives a lot of information, but it's best if complemented with some molecular level technique that allows to have, be it spectroscopic or otherwise, to have some molecular characterization for confirmation. But I am definitely convinced that precise modeling along geochemical models of adsorption would be very useful. And that's one of the things that specialists in the origins of life do not know much about usually. What do you think? And the other one? It would be, it's molecular modeling. That's what you are talking about. And that's certainly also a useful complement to other sources of information. In my experience, it's best when you already know quite a few things about the system and you hypothesize that such a reaction is taking place on such a surface site so that you know exactly what you want to model. If you want to start anew for a completely fresh problem, there are just too many things that can happen. And I remember studying the formation of nucleotide from the base and from an activated form of ribose. And we had a very good experimental team with Marco Saita, and we demonstrated that it was possible. When we tested it, we saw that it happened indeed, but also minority, because at the same time there were some degradation reactions that destroyed the cycles, and we had not thought of modeling them. So it's certainly very useful, but I would say the last stage of understanding, but there is a different class of theoretical models, like those of Stuart Kaufman, who said, let's imagine that we have a set of reactions, and let's write a graph of catalysis, and some products will catalyze other reactions, and let's see how it evolves kinetically. That's not a quantum level, that's more like a classic kinetics, but for very complicated systems. In this case, it's so complicated that it has never been observed experimentally. So there is always the risk when you are using only a theoretical approach of being completely divorced from reality. But I think that's not the case for you and your team, because you are making experiments.
And also, if I could just make another one. I was interested in asking you about the use, well, you and many other vanguard scientists talk about the clays and the potential of prebiotic chemistry of clays, but I was interested in asking you about the potential of other types of minerals, such as olivine and nesosilicates that appear in the unit cell. It's an orthosilicate. It's like a cereal box, but when we look at the actual natural crystals, I don't want to use the word amorphous, but they don't have a clear habit like pyrite and apatite that are hexagonal and cubical respectively. So in the case of these really rough surfaces and also high proton zero net charge surfaces, would you be willing to say that they have some potential in these experiments?
Certainly. And, there are so many possible prebiotic minerals that you cannot possibly test all of them, but it's very important that some people just keep doing it. Regarding clays, I have mentioned clays many times because many people have studied them, but I often wonder how much is determined by cultural factors, like the story in the Genesis of God blowing on clay to make man. Because for amino acids condensation, for example, amorphous silica works definitely better than most clays. But once again, and I think in the case of nucleotides, and I had a discussion this morning about it, but I completely agree. Nucleotides polymerization can happen on clays, but not on any clays. You have to study in very fine detail exactly if it's a swelling clay or non-swelling clay tetrahedral or octahedral substitution, the degree of substitution, the charge per unit cell. So you need really to do some precise surface chemistry. And I think possibly you would agree if you have talked with biologists in this field, they don't realize how complex surfaces can be. And for them, a clay is a clay is a clay. Regarding olivine, yes, that would be a good idea. For me, I do not use it simply for a technical reason that it's difficult to obtain it with a high surface area. And that's of course easier to characterize as solid molecules when there are many of them, and so when there is a high surface. But if you can do it, certainly.
Thank you very much.
Thank you, doctor. Thank you for your time and your very interesting topic. Thank you.
Thank you.
Thank
you.
Por favor, los invitamos a que continúen con nosotros. A continuación nos acompaña la doctora Meli Cornet de la Embajada de Francia y nos hablará sobre becas en Francia. Por favor, démosle la bienvenida.
Sí. Hola, buenas tardes a todas y todos. Solo le voy a robar como 5 minutos porque sí que sé que ya llegó la hora de comer, ¿no? Así que aprovechando la presencia del doctor Lambert, solo para, pues si les interesa seguir, por ejemplo, haciendo estancias científicas en Francia o un doctorado en cotutela con Francia o más tarde como estancias científicas como investigadores, solo les voy a presentar rápido como los programas que manejamos y a la ayuda y al apoyo que pueden recibir de la Embajada de Francia en México para asistirle en sus proyectos de colaboración con Francia, ¿no? Así que pues, ¿no se ve? Sí. Sí, pues primero me presento, en efecto, yo soy la doctora Amélie, yo soy la agregada para la cooperación científica y tecnológica para la Embajada de Francia en México y también para el Instituto Francés de América Latina, aquí en México. Y tenemos todo un equipo de apoyo a las movilidades a nivel de estudiantes y de investigador. Yo me encargo más precisamente de los estudiantes de doctorado y de los investigadores, pero también tenemos todo un equipo de apoyo para los estudiantes desde la licenciatura hasta la maestría. Así que pues aquí estamos en México. No, me imagino que sí saben que hay una oficina de Campus France en México, pero también para que sepan que hay otras oficinas a través del país. Y las oficinas de Campus France en México son las oficinas de la agencia Campus France, que es una agencia del gobierno francés para apoyar la movilidad estudiantil hacia Francia. Así que pues solo para darles algunas herramientas para buscar o programas de becas o programas de titulación en inglés si no hablan todavía francés, o programas pues solo de maestría o licenciatura, pues tenemos varias herramientas o online, o también lo pueden encontrar dentro de la oficina Campus France, que aquí en México está en la Casa de Francia, en la colonia Juárez, y pues tienen varias websites o libretitos también que les explican dónde encontrar las informaciones. Por ejemplo, si buscan una beca pueden ir a Campus Bourse en el internet, también existe en español. Hay la plataforma Mon Master, que es también la plataforma para buscar un programa de maestría en Francia. Y pues también hay recursos sobre cómo hacer los trámites de la visa, cómo vivir en las diferentes ciudades estudiantiles de Francia, porque obviamente todos conocemos a París y tenemos un muy buen ejemplo de la Sorbonne Université acá, pero por supuesto hay también muchas otras ciudades estudiantiles en Francia que son muy agradables de vivir y que tienen universidades de muy buen nivel. Y pues sí, como lo acabo de comentar, hay también una página web para buscar programas de becas y también para que sepan que en la Embajada de Francia aquí en México también manejamos programas de becas para estudiantes al nivel de maestría y también para estudiantes de cotutela entre Francia y México, así que no duden en mandarnos un mensaje. Yo voy a dejar, aquí también hay todos los contactos de las diferentes oficinas de Campus France. Así que si necesitan una cita para hablar de su proyecto de estudios en Francia o unas informaciones sobre las becas, pues también les pueden escribir. Y sí, eso es el equipo de Campus France aquí en todo el país. Y también les quería invitar al evento que organizamos en mayo próximo, que se llama Tu Doctorado en Francia. Va a ser en la Ciudad de México el 23 de mayo en la Casa del Tiempo en San Miguel de Chapultepec. Sí es una casa de la UNAM, pero está abierto a todos los estudiantes de la Ciudad de México y del Estado de México en general, si se animan a venir a la Ciudad de México. Y durante toda la tarde van a hacer conferencias sobre cómo hacer su doctorado o 100% en Francia o en cooperación con Francia en el marco de un doctorado en cotutela. También van a hacer conferencias sobre las diferentes posibilidades de becas del CCT y también del gobierno francés. Y van a ser la oportunidad de encontrar y de hablar con los representantes de las universidades francesas que van a estar acá. Vamos a tener por lo menos 8 instituciones francesas. Va a ser personas de la Sorbonne Université. También van a ser personas, por ejemplo, de la Universidad de Lyon, del Instituto de Ciencias Analíticas, también del Instituto Politécnico de París. Así que si quieren venir, ver a las universidades, también hablar con los representantes, que no solo son representantes de la universidad, pero más que todo son investigadores y pueden hablar de proyectos de investigación conjuntos que les gustaría hacer. Y pues ya, nada más para decirle gracias por escucharme y que no duden en contactar o contactarme o contactar la oficina Campus France y les esperamos. Muchísimas gracias.
Muchas gracias. Pues a continuación, para cerrar este evento, los invitamos a escuchar a nuestro compañero Alejandro Paredes. Dr. Lambert, we invite you to listen to Dr. Alejandro Paredes, who will perform some musical pieces of his own. Una breve reseña sobre el doctor Alejandro, en lo que esperamos a que prepare su equipo. Ay, perdón.